In the previous video we looked at the graph of y equals sine of x, and that's what I'm going to start with here. So I'm setting the number a to be equal to 1 and the number b to be equal to 1, so we just get sine of x. We saw that the range of sine of x is from -1 to +1. We also saw that the period of sine of x is 2 pi. So we can see that here. 2 pi is the interval over which the function repeats itself. It's the smallest such interval. Now let's change the value of a. So we're changing the number in front of sine. So if we increase a, you can see what's happening. We're increasing the range of the function. So for example, when a is 3, we see that the range is from -3 to +3. So basically we're multiplying all the values of sine of x by 3. So when a was equal to 1, if I go back to this, say for example when x is pi over 2 or 90 degrees, the sine of 90 degrees is 1. Well, if we multiply 1 by 3 we get 3. So the y value of this point is multiplied by 3, so it goes up to 3. Similarly over here, the sine of 270 degrees or 3 pi over 2 radians is -1. If we multiply -1 by 3 we get -3. So we're multiplying the y values of all the points by 3. So the range is from -a to a. So if a is 3, the range is from -3 to 3. Notice that the period doesn't change. The period is still 2 pi. Now of course we could take a to be a number less than 1. So I'm decreasing a back to 1. Now let's make it smaller, say 0.9, 0.8, 0.7. So for example, the sine of 90 degrees is 1, but if we get 0.6 of that, we have 0.6 here. So the range is from -0.6 to +0.6. And of course I could bring this to 0. So now we just have the graph of the function f of x equals 0, which is just the x-axis, just a horizontal line. Now what happens if we make a negative? Let's bring it to -1. We've actually turned the graph of sine of x upside down. We've reflected it through the x-axis. So we have the graph of minus sine x. Let's bring it back to +1. So here is the case when a is +1. And here is -1 again. A equals -1. So by changing this sign, we are just reflecting the positive function through the x-axis. Y values that are positive become negative, and y values that are negative become positive. Now let's change b. b is the number in front of x. Let's increase b from 1 to 2. We can see what's happening. I'm keeping a fixed at 1. So the amplitude is 1, or the range is from -1 to 1. So now I'm changing b, increasing b to 2. And notice that the graph is getting compressed in the x direction. Now let's consider the period of this function. That's the smallest interval over which this function repeats itself. We can see that it's not 2 pi. The function will repeat itself over 2 pi, of course, but we see that it repeats itself over a smaller interval, actually from 0 to pi. So now we have the graph of sine 2x. So by doubling the value of b, we doubled it from 1 to 2. We've actually halved the period. The period went from 2 pi down to pi, or 180 degrees. Now we have a formula for the period which I'll discuss later. To get the period, we take 2 pi and divide it by b. That's the coefficient of x here. So if b is 2, we have 2 pi divided by 2. Well, 2 pi divided by 2 is just pi. So increasing b will decrease the period. Let's increase b further. So we can see that the period is getting smaller. Now when b is 3, we can see the period is 2 pi over 3. 2 pi over 3 is this distance here. So I'll continue on increasing b up to 4. So now we have the graph of sine of 4x. So the period is 2 pi divided by 4. Well, that's just the same as pi over 2 if we cancel this down. So here we can see the period. So this distance here is the period, the smallest interval over which the function repeats itself. So now I want to prove that for the function ASinbx, the period is 2 pi divided by b. Now let p be the period of this function. Now here's the definition of the period of a function. If we work out the function at x plus the period, we get the same value if we work it out at just x. So for example, if our function is just sine of x, as we saw in the previous video, the period is 2 pi. Let's take some value x and consider the f of x. Well, we just go up to the graph or down to the graph depending, and we go across here and we have f of x, of course. Now if we add 2 pi onto x, we will end up over here. So this point is x plus 2 pi, or x plus p. So the period here is 2 pi. So if we go up to the graph, we get the same value as f of x. So for the sine function, f of x plus 2 pi equals f of x. So now let's get back to the function ASinbx, where b doesn't have to be 1. Well, using the definition of the period of a function and equating these, we can cancel the a's, so we can see that the period is not affected by the amplitude, as we saw before. Multiplying b in here, we get sine of bx plus b times p. So all I did here was replace x with x plus p when getting f of x plus p. Just replace this x with x plus p and then multiply b in. So this must equal sine of bx. But we know that the sine function has period 2 pi, so adding 2 pi onto this angle won't change it. So if this is equal to 2 pi or 360 degrees, we're not changing the value of the sine function. So in other words, sine of bx plus bp will equal sine of bx when bp is equal to 2 pi. So it's just like we have this angle here, we're adding 360 degrees onto it, so we're just taking a full revolution. So we're back to where we started from, if you like, and getting the sine is not affected by that change. We could also add, say, 720 degrees onto this, onto bx. Any integer multiple of 360 degrees won't affect the value of the sine function. But of course we're interested in the smallest value here. That'll give us the smallest interval over which the sine function repeats itself, and the smallest value that we can put here is 360 degrees or 2 pi radians. So if bp is 2 pi, we see that p is 2 pi divided by b, and that's what we had to prove. So when you get a function of this form, you know that the period is 2 pi over the coefficient of x. Now I just want to explain the graph of sine of x for negative values of x. We know from a previous video on negative angles that the sine of minus x is minus sine x. So for example, if x is 90 degrees, then the sine of minus 90 degrees is equal to minus sine of 90 degrees. So if we know the sine of 90 degrees, or pi over 2 radians, well, that's plus 1. We can get the sine of minus 90 degrees. We just stick a minus sign in front of the sine of 90 degrees. So the sine of 90 degrees is 1, that means the sine of minus 90 degrees is minus 1. As a matter of fact, we can get this point here from this point here geometrically by reflecting this point through the origin. So by getting the image of this point under central symmetry in this point, we can get this point here. Functions with this property are called odd functions. In other words, functions that have the property that f of minus x equals minus f of x. Now let's look at the graph of a cos bx. In the previous video we looked at the graph of cos of x. Well, we looked at it for positive values of x. Here we see it for negative values of x also. We saw that the period of the cos function was 2 pi. Now, just like for the sine function, we can change the amplitude. We can change a, and we can see how it affects the range. So it's in the same, just like before. We stretch or compress the function in the y direction. So I'll bring it back to 1. And we can also change the period by changing b. So since the period of the cos function of cos 1x is 1, we can prove, just like before, that the period of a cos bx is 2 pi divided by b. So if I make b equal to 2, we see that the period is 2 pi divided by 2, or pi. We've halved the period, just like for the sine function. Now I'll just show the sine function alongside the cos function. The sine function is in red. They both have exactly the same shape. As a matter of fact, we could shift one of the functions either to the left or to the right, and it would fit exactly on the graph of the other function. As a matter of fact, if we shift the cos function by 90 degrees to the right, the blue curve will fit exactly down on the red curve. And if we shift the red curve, the sine function, by 90 degrees to the left, the sine function will fit exactly on the cos function. I'll explain more about that in another video. Finally, I just want to briefly mention the graph of cos of x for negative values of x. Let's take 180 degrees. Now, the cos of 180 degrees, or pi radians, is minus 1. However, the cos of minus 180 degrees is also minus 1. We saw in a previous video that the cos of minus x is just the cos of x. So this is in a video on negative angles. If you want to look up the proof of this. The proof involves the unit circle. So here we're getting f of minus 180 degrees, or the cos of minus 180 degrees. We see it's just the same as the cos of plus 180 degrees. So we're just letting x be 180 degrees in this example. So the cos function has the property that f of minus x equals f of x. Functions with this property are called even functions. So if we know the graph for positive values of x, we can easily get the part of the graph for negative values of x by reflecting this part of the graph through the y-axis. So we just reflect this point through the y-axis. So we get the image of this point under axial symmetry in the y-axis. The same goes for this point here. Say this is x, and we want to find the value of the function at minus x. We just reflect this through the y-axis, and you see we get the same value, f of x equals f of minus x.